This is Lab 5, the human rocket. The objectives of this lab were to model the position versus time and velocity versus time of Felix Baumgartner's free fall from over 38,000 meters that broke the speed of sound. Consider an appropriate model of air resistance for a fall from such a height, and discuss the effect of temperature and air density on the free fall. Important principles were Newton's second law, which was used to update the velocity and the position. In the free fall, Felix Baumgartner fell from a height of 38,969.4 meters in an attempt to break the sound barrier without the help of an aircraft. His max vertical speed was 377.1 meters per second, achieved at a time of 50 seconds. His total time of free fall was 4 minutes and 20 seconds, and he deployed a parachute at 2,567 meters. The lowest temperature recorded for the run was 202.1 Kelvin, and the weight of him plus his device was 117.934 kilograms. In order to model the drag for the system, I used the equation 1/2 rho v squared times c sub d times a equals m times g. For v, I used the max speed achieved, which was 377.1 meters per second. For rho, I found it by using an online calculator to find the air density at the height at which the maximum velocity was achieved. And then I solved for c sub d times a, which I used as the coefficient for drag in the code. In order to change air density rho in the code, I used the equation P equals P naught times 273 over T times e to the negative P naught times G times H over capital P naught. In order to change temperature, I used the starting temperature and the final temperature, which was found using an online calculator for the given altitudes. I used the difference between those two temperatures and divided by the total time to find delta T for temperature. However, I also found a graph showing that temperature does not change exactly linearly. It changes in this weird shape, but I could not figure out how to model that within the code. In the code, I put in the initial conditions for mass, position, delta T for temperature, the initial temperature, the air density at sea level, the air pressure at sea level, G, and the coefficient for drag. In this line, I put in the equation that updates rho, and then here's the gravity. Here is the force of drag, which is the equation from earlier. And then these two lines are Newton's second law to update velocity and position. And these two lines update time and temperature. When the program is run, it gives a position versus time graph and a velocity versus time graph. In the results, the graph showed that the final position was 2,233.25 meters. Actually, it was 2,567 meters where the parachute was deployed. The graph showed the max speed as 308.878 meters per second. Actually, it was 377.1 meters per second. The differences here are likely due to temperature being modeled inaccurately, which also affected air density. In the actual run, the sound barrier was broken at 309.7 meters per second at 34 seconds, which is actually possible as shown by the graph in the top right, due to the sound barrier, the speed of sound being lower at higher altitudes, which is affected by temperature and air density being different at higher altitudes.